So, let's kick it right off. In this talk, I'm gonna talk about Akka. The talk is kind of a both preview, but at the same time it's a review of what it actually is. Often when I talk to people, they think they know what Akka is, maybe they've heard about like one or two things, have not really dived into it. So this talk kind of explains also what it is, how we think about things. The joke here is that cheers from the friendly volcano close by, because I'm now located in Japan. So, disclaimer is that this is not a strict roadmap, so things could change. My name is Konrad Malawski, work on the Akka team since a few years. I also did the Reactive Streams TCK, participated in that entire process, and also part of the Scala language, Scala library improvement process. So things like that. Recently named Java Champion. Yay. In Poland I run, did I disconnect the thing? No. I run a conference called Geekon. This time the 10th edition of it, so we're super excited. But let's jump right in. So, the underlying motto of our team is really, can we do better than that? There's some status quo, and how can we improve it? But also, been there, done that. It's completely wrong, or been there, done that. Yeah, maybe there's something there. So a lot of the things you'll see here, as I go from past to present of Akka, you'll notice first circuit breakers, etc., etc. That's been there for many years, and we kind of learned where they work, where they don't, etc. So with Reactive, obviously, Akka being a reactive toolkit, before the kind of term was that trendy, I guess, even. Starting with the Reactive Manifesto, of course, which our CTO wrote, Jonas Bonnier, and kind of to explain what was talked about here during this conference, that was more about reactive applications, and I think that's not even half of the story. That's a small little piece of the pie, because it's really about reactive systems, how multiple apps interact with one another. I need to do something with the mic, sorry. It's kind of sliding down. Okay, should be better. So, especially when we talk about you have some microservices, or maybe you don't even have microservices, but you have a number of apps, and they somehow need to interact with one another. It's about systems. It's not about just one app, which, okay, internally it does some stuff on features. That's not really helpful. So, how we look at it is there's the inside of your app, and when I say that, I don't mean a box. I mean, could be any number of boxes, physical or virtualized, but it is one single service, so it provides one functionality. So it could be a microservice in terms of, okay, it's only the service which you post tweets to, so the functionality is very basic, but internally there's a lot of traffic and a lot of shuffling around bits to get the thing done. So internally you want to be as fast as possible. And you can do different trade-offs then with your public-facing APIs. Public-facing APIs, people do want JSON, people do want HTTP. And that's nice, that's human-readable, but it's also slower than you can pull off things with binary fast encodings and other protocols than HTTP. So this is what we think about with Akka messaging. So Akka messaging, it's our own protocol. We push around 1 million per second, if you want, between two boxes. And externally, we would expose some JSON interfaces, or whatever people would want, right? I wrote a mini book about it, if you're curious, why Reactive. It's available for free from O'Reilly. It's like 12 pages going deep dive into this concept. So I would like to know if people have heard about Akka at all before this conference. Okay, and when saying that, do you know about the actors, or you know we have a lot of different stuff? It's mostly about the actors, right? When people have heard about Akka, it's this concurrency, distributed systems thing, I guess, right? Okay, but many people have not raised their hands. So the quick intro is that it's all... Jesus, this mic. So it's all about this message-driven kind of philosophy behind the actors and behind the streams and behind everything we do. And this allows us to build the same style of app locally on a single machine, and turns out, okay, it runs nice on a multi-core machine, but the same app can then be easily distributed to a multi-machine cluster. And we do it not the way like RPC frameworks do, which they make it look as if these remote method calls, they look like method calls. We make it the opposite way. So we make everything look as if you're sending a message, which is more natural to the network and maybe less natural for like daily development, what you're used to. But then going distributed is just so native feeling. So, where did it really start? So Akka founded 2009 by Jonas Bonnier here. And back then it was, had all the buzzwords. So it was, RESTful, distributed, persistent, all the buzzwords that were trendy then, and some of them are still now. And the core of it is this actor model. So the actor model is really a concurrency concept, a concurrency model. And it says that we model everything as an actor. So instead of threads, we talk about actors. Actors are a lightweight kind of alternative to threads, conceptually at least. Conceptually, because in runtime there is threads, right? And actors run on threads, of course, but conceptually you can think of it as the thing that performs the work. And they basically can only do these things. They can send messages, they can change their state, or they can create other actors. And everything in Akka is modeled as that, and all the other abstractions are built on top of that. And turns out this is a really powerful abstraction for building high-performance systems, because there is minimized sharing of resources, minimized mutating of shared state, because there is none, and it makes the programming model also very easy to distribute, because you have a message, you serialize the message, you send the message over the network, done. The only thing that can happen and go wrong is, well, the message didn't arrive, and there's only one failure mode in the entire model. Whereas with RPC, it's not as native feeling. So we model both concurrency and distribution as the same thing. How does an actor look like? If this is your first time looking at an actor, so I'm showing Scala code here, but we always have Scala and Java APIs, so I'm going to show Java APIs as well, if you're not familiar with Scala. But the basics are really simple. It's just extends actor, override receive. If you receive a read temperature, you reply to the sender with some temperature. This is how it would look in Java, if you're curious. So a bit more boilerplate. You create a receive, some matching facilities, because Java doesn't currently have pattern matching, so we built some that makes it feel a bit more native to Java people. And it could be across threads, could be across network, etc. Now, this is very interesting, but it's not all there is to it. You can do more than request response. You can send a message to someone that they should tell some other actor. So it's not a request response. There is no response to this interaction. Because response also costs, because you need to push some bytes onto the network, right? So you need to do something. So if we can avoid a response because we don't need one, we can get away with communication patterns like that. Another thing, as I talked about this inside-outside story, is a friend of mine once said that the internet is running in debug mode, by which he thinks about the textual representation and the HTTP calls, etc., which are kind of very verbose, right? So imagine you have such a data type. You don't have to look at it very precisely, but serialized by one of the binary serializers. That's the timings. So in nanoseconds, so pretty fast, tens, maybe 100 max, to create and serialize such a thing, and the size of it, right? When we talk about XML serialization of that thing over Java serialization, you talk about much bigger and much slower serialization times. And I will probably destroy this mic at some point. So, An example of how that looks in action is you have such a case class that's just a data type. It has these fields like an ID, description, total cost, etc. And if you serialize it with Java serialization, that's going to be as big as that. It does carry type information, so that's good. However, it's pretty big, and whatever is big costs transfer and costs time. Even XML serialization of that same data type would be smaller than that, so let that sink in. JSON, similar. The trade-off is, of course, that it doesn't carry any type information, right? Here we have the types serialized as well. Here we don't. But with binary serialization, we can get both of carry some types if you have like try or something like that, or with protobuf, it's then encoded in an external definition of the protocol. So it's not on the wire, but it is still strictly defined in the protocol. So historically, we did use Java serialization quite a bit, and nowadays we don't, but for kind of compatibility reasons, for allowing people to do just rollouts of new updates, we don't disable Java serialization by default, and I would recommend you do so if you try Akka in a serious setting. If you just play around, doesn't matter, but if you're doing anything serious, do turn off Java serialization. It's as easy as that. Performance change is really you get anything from a 5x to a 10x from just changing one serialization mechanism to another, because really it ends up dominating the communication patterns. Like most of the time will be spent serializing, deserializing stuff if you have a nice fast messaging framework. So, side note, maybe less interesting for people here. This was a slide more for Java and for Scala people who were complaining about, ooh, but you always break compatibility. Well, we haven't broken compatibility since a number of years, and we don't foresee there's any feature coming that will make us break compatibility. So that's interesting for you to know if you're willing to bet on Akka and the binary protocols, right? All right, so futures. That's a fun side note, which is going to lead into why we introduced circuit breakers. So initially, Scala didn't have its own futures. And, well, then basically every library on the planet introduced their own futures. There was Twitter futures, which are still out there, the only difference being cancellation, I believe. And there was a number of future implementations. Then everybody got together, implemented one, which most libraries agreed on, and that's now the Scala futures. Basically, the bigger part of it was based on the Akka futures that we had back then. So of course we had the futures there, but then when you do this asynchronous operations, you get into situations where you start needing circuit breakers, even locally. So we introduced circuit breakers. Okay, we have futures, we have circuit breakers, and here I would like to explain that I think that best practices, in this case, slapping circuit breakers on everything, is maybe a solution to yesterday's problems in terms of we didn't know any better, and nowadays when people talk about circuit breakers, I think it's overhyped a bit, and we've learned this the hard way. It's not a solution for everything. It's not a substitute for proper flow control. It helps you when stuff is failing, but you should not be relying on circuit breakers to have everything run smoothly. That's like two different things. One is have things run smoothly, and one is, okay, things are failing, I need to back off. That's not exactly the same thing. Circuit breakers in action, you get a lot of requests, you can't handle it, you start replying maybe 500s or not replying at all, and then the circuit breaker trips and will delay sending requests until some timeout or some other mechanism opens the circuit breaker again, closes the circuit breaker again, at which time you're going to be sending requests again. So this is why I think this is why I say this is not the optimal way to think about like flow control in the system, because it works like having a Ferrari, crashing it into a pole, building a new one or buying a new one, then crashing it into a pole again, and then again and again and again. It's a very, such a waste. Where we could do something better than that, and this is what later leads us to reactive streams, which I'll talk about. So, and the other problem is the timeouts. So the timeouts usually in circuit breakers, what I see people do at least, is they're one or the other way hard-coded, same as timeouts. If you have asynchronous calls or you're expecting some of a service to complete within some given amount of time, it's more or less a guesswork, and people would try to make these timeouts to be such that they would meet their SLAs even with failures happening, but there's still too much guesswork in it, I think. I haven't seen a real system with like self-adapting timeouts and things like that. If anyone has seen one, would like to talk a bit. So, this will read into Akka Streams and Reactive Streams. So we talked about actors. We do this distribution mechanism. It's also a membership protocol. So we have an Akka cluster mechanism, and sometimes when I say cluster and people have been exposed to application servers, they think it's a cluster like an application server cluster where you replicate sessions or something like that. That's not at all what we do. It's more of an Erlang model where the application is distributed. It's not that, okay, we replicate some piece of state over there. The actual running thing is over there as well. And then we route messages to the right nodes, achieving nice throughput and locality for any kind of request you may be sending to the cluster. In practice, this works like that. So very in the abstract, you have a message K5, it goes into the sharding subsystem, and it goes to the right actor. Even if the actor was living here, but the node died, we are able to replicate the actor, and I'll talk about how we deal with state. And it will seem from the outside that even if this thing failed, no one ever knows about it on the outside. So this is our way of dealing with resilience. Internally, of course, there's heart beating and other mechanisms to figure out if a node is actually dead or not. So, forwarding a bit. So, how do we deal with the outside world, right? Because that was all Akka messaging, that's this internal custom protocol, binary. But how do we deal with the outside, which usually is HTTP? So, we have a full HTTP server implementation. So, it's not just some DSL on top of some Jetty or something. It is a full server implementation from all the sockets, all the way up. And the reason we did that is because it's a streaming-focused HTTP server. And to be able to actually do the full back pressure from socket to application layer, we need control of all the layers. And I'm going to show an example how that works. And we also do WebSockets and HTTP2 as well. I'm going to show an example. So this is jumping forward a bit, but you've seen kind of Spring's version of that, which is for fluxes, etc. We call them flows, sources, and sinks. I think the terminology is maybe a bit better. So a flow basically is like a function, but it's streaming, right? It can get multiple requests in, it can get multiple requests out, right? And it also can, for one request, send multiple responses, which funnily enough is exactly how server push is modeled as in HTTP2. So this type represents exactly what a server in both HTTP and HTTP2 is. Then the entity can be a source of bytes, and the WebSocket is basically the same but declared on messages. Routing API, it's a bit different than what you may be used to from Java land, but the upside is you can nest these, we call them directives, and it means that on a path hello, if it's a GET request, complete with this and that. And here we have a lot of sugar that you can easily complete things with. And this is an entire HTTP application. Now the upside is, if you make any kind of mistake, you will try to return a type that has no serialization defined, it will not compile. So we fail really early during compilation phase in such things. Whereas more of a Java style with annotations, you would fail in runtime, right? So it's a bit nicer for development, I would say. Like, however fast you can catch errors in development time, in compilation time, the less debugging you have to do later on when some code path has failed to a weird reason. There's also a low-level API because this is the high-level API, if you were to use Akka HTTP directly to write your apps. But many people don't do that actually, and they just use Play, right? The Play framework sits on top of Akka HTTP, and it doesn't use this high-level API because that, of course, has some overhead. It uses a low-level API which just gets the objects, the requests and responses. So this slide I added because in the previous talk Mark was showing basically what I showed a few times, which is this reactive streaming example, right? And I think the main point was missing in the last talk, which was the back pressure. The reason we did reactive streams is to do this flow control, right? We talked about, okay, we didn't really manage flow control, we just did circuit breakers. So what is this flow control? How does it actually show in a real application? So I said that we have the entire stack in Akka implemented, right? So we own all the sockets, all the when we push to them, when we don't push to them. And we also own the Akka Streams layer, which is basically pull-based. So if we know that we will not be able to send data to the network, we will not pull from the application, which means some tweets, some rendering will not even be triggered because there is no need to do it yet. So you can imagine that you're Twitter, you're streaming some tweets, and this is the network, so someone is on their phone getting the tweets, and suddenly they go offline. They go into a tunnel or something. So here I have an example app. I'm not going to show the app, I just want to show the back pressure kicking in. And I'm going to curl the tweets here, and it just streams this hello world example tweet thing. Over here we can see the operating system's send and receive buffers. So that's the receive queue and that's the send queue, right? So the server is pushing into the send queue, the operating system takes from the send queue, pushes onto the network, and the opposite on the other side, right? So bottom line, client, top line, server. And now if we pause the process that was reading things, you'll see the send queue gets full, well, the receive queue gets full, then the send queue gets full, and then we stop even generating the tweets on the server side, which can be seen. I didn't do printouts there, but basically, you see that huge spike there? That spike was us generating the tweets. We were doing stuff. And when I paused the app, it just goes down. And when I will resume the app, so foreground 1, everything resumes. We drain the receive buffer, we drain the send buffer, application starts generating tweets again, and yeah, CPU will be again doing stuff. See, spike is back. So this is what Reactive Streams is about. It's about not doing work and not sending data when the other side is not ready to receive it for some reason, like buffers being full, network being unavailable, etc. And the nice thing about Reactive Streams is that it's a spec about, it's a vendor agnostic, right? So we did this collaboration, everybody implements the same thing, so it doesn't matter what libraries you're using. This would still work if they implemented Reactive Streams correctly. So yeah, I thought that's the key feature that was kind of missing. Do people do that? Yes, absolutely. Probably not in the exact same way as I just showed, but in Twitter APIs you have these stall warnings. And stall warnings basically mean that if you're a client and you're reading too slow, you will get these warnings that say, hey, you're falling behind, we've allocated this much buffer space for you, but you're reading so slow that we're forced into buffering more and more stuff, so if you don't speed up, we will just kill the connection because, you know, you're making us buffer too much. So making flow control and buffer space explicit in the application layer is super powerful, and building such APIs suddenly becomes a two-liner. You basically do return source, you're done. It just works. So I thought that's a neat feature to kind of highlight. Why do we do a full server implementation? Exactly that's why. So we talked about actors and how they migrate between the nodes if a node fails. But I also said that we don't magically replicate the state. This would be kind of scary, right? To randomly send some live applications data to some other nodes for them to maybe use it if they were forced to restart an actor. So what we do instead is event sourcing. Have been doing that. Was my first big project when I joined the team. So like 4 years in core Akka, before that a number of years as a community project. And the general idea is, if you think about actors, we only talk in messages, right? There's no way to call a method on an actor. And basically, if we were to persist the effects of these commands, so the incoming stuff we call commands, the things you persist we call events, kind of event sourcing technology, terminology, and we just persist them in some replicated data store, usually a Cassandra, or if you're a small scale shop, it could be an SQL store, could be Mongo, anything you like. And then once an actor recovers, it knows its identifier, goes to the data store, it says, hey, what's my last state? And now again, this is still just messages. It's not that there's some blob of state that it gets, it loads into memory and it's done. It still gets all the messages that it was acting upon previously. Because what you do is you get a command, you transform it to an event, basically you do the validation. You get a command that says, give me money. So you check, should I be giving that person my money? Yes, no. And then you persist this as an event, and you basically get this message, this event, which is a message, to yourself again, and you act on it. So this recovery thing is exactly the same as normal operations. It's indistinguishable from the normal, how you would normally write the thing. There's no special codes to be written because it's again just messages. And the additional thing we're able to do here is to guarantee consistency of the state is, because the state is reconstructed, once you're done replaying all the events, you have your state because you've basically logged who I have given money to, how much I have received, etc. So you build up your state. And then during the time you're doing the replay, you could have been getting commands at the same time, right? So it would be unsafe to reply to people based on partial information while you're still replaying. So we handle that, and basically, because we know how many events are in the store, we apply these events, and during that time we buffer all incoming commands from the actor, and only once you're done recovering, we send the commands into the actor and it can, again, normal operations. You would notice in logs that it has failed, it has appeared again, it did the replay, but from a logic point of view, it's exactly the same as normal operations. So this is why messaging is so important, I think, as the core concept. This is the API, if you want to look at it. I propose looking at APIs afterwards. If this stuff is interesting to you, you can just look it up. Again, we have Java, Scala APIs for everything. Try to make it as nice as possible for both languages. So, future, finally. So, the Akka persistence side of things really takes the consistent side of things in the cap theorem, right? So it's really consistent, it's partition tolerant. We guarantee that by the single writer principle. So there's always one actor for a given ID, and this way we can guarantee that it's always consistent. The other side of the medal is always being available, even with maybe some outdated information. So for that, we built recently the distributed data module. Has come out last year, but this year, basically making sure it's all nice and dandy. Basically all stable now. Nothing gonna change there, I think. Again, API, if you're curious about these concepts, the usual APIs we have, all such libraries have are counters, various types of counters, sets, maps, and combinations thereof. And again, because this is all messaging, and we have multiple nodes, so this is a counter example where each of the nodes can update the counter individually. Internally, this is represented as each node having its bucket in the counter. So node 1 updates the node 1 bucket, and the total count of the counter, well, the value of the counter, is basically the sum of all the updates here, or the max, depends which kind of you wanna have. And we basically can just replicate this message which represents the state, or we can just replicate the difference of a state. So we have two states. Imagine you have two nodes, they both did updates. You make a diff out of them. And this is all done internally. You don't need to care about it at all. We do a diff, we see which values have changed and only transmit that. And again, this is nice and safe because the only thing that can happen is, okay, the message could not arrive because maybe node 1 crashed or node 3 crashed, etc. But eventually, because all the nodes have these updates locally and they keep gossiping, all the nodes eventually get all the updates. And again, transparently and enabled by being message-based. So, finally streams. So I showed streams already. There's this kind of catch-22 with Akka HTTP and Akka Streams, because one uses the other, and they were also developed at the same time. So we basically, so Victor was inviting people to join Reactive Streams back then. We did this initiative, and joined by Pivotal, Red Hat, Oracle people, so Doug Lee was involved, Ben Christiansen from RxJava, like lots of people joined in. And yeah, this is just me complaining that the word stream is a bit overloaded because half of these technologies are not even streaming things. And also it's a bit misleading. This is Scala detail maybe, so let's skip that. Basically, when we say streams, we mean exactly this terminology, which is, it could be an infinite data set, doesn't have to be, but could be, and it's an element by element. So again, think about messaging and not like TCP, where you have an infinite stream of various chunks of blobs, right? So more like UDP, not like TCP. And it's designed to be asynchronous. That was the goal of the spec from the beginning. So where Akka Streams fit, and sometimes people ask, okay, but I have like Spark streaming, or I have the Java streams, whatnot. All of them are completely different and sadly share the same name. So when you have JDK's streams, like the dot stream on collections, it's more like bulk collection API really, because it works on the given collection. So it's not really the potentially infinite thing. Could be, but usually isn't. And also, to get the things out of it, you have to have this collector. So it's also this point where you have to stop, block, and start collecting. Whereas we are fully asynchronous, and unlike the Spark streaming case, which is more for data processing, and you start at Spark cluster and you submit the job, this is intended to be in the hot path. We built an HTTP server on it, right? This is the kind of use case. Yeah, here I compare it to various other things, but I suppose we can jump over it. As I said, the Java ones are more like collections, really. And reactive streams are now included in JDK 9. So when people talk about reactive streams, it's good to know what it is, but if you have a choice, you can just use the JDK 9 one. And the thing is that it's exactly the same interface and exactly the same semantics. So basically it was developed as a proof of concept outside. We've proven to the community and to Doug and to Oracle that this is a good idea because everybody adopted this technology, including us, the Spring guys and the Red Hat guys. And then it got included into JDK. So if you see the Java util concurrent flow, now you know this is the reactive streams thing, which allows you to do this back pressure flow control semantics. And as said before, you shouldn't be really implementing reactive streams or JDK flow directly, rather rely on someone else doing it for you. And the reason I'm saying it is, it's not really an API. Sadly, it used to be even called an SPI in the package name, that got lost during some debates on that. So let's jump right into it, right? It's fast publisher, slow subscriber. How it works is basically this managing of how much you're allowed to push, right? This is what we've seen in action with the TCP example, with the tweets. Basically, we were not sending, well, Akka was not sending this request parameter, so the server side said, well, okay, I can't send any more data, so it was not generating any more data. These are in the interfaces, exactly the same in JDK as they were in reactive streams. And these are the rules that govern these 4 interfaces, because people in presentations always say, oh, look, it's 4 interfaces, so simple. And they look simple, right? You look at subscription, that's what is given from a publisher to a subscriber, and it says, oh yeah, requests, number of elements, or cancel. Oh yeah, how hard could it be? Turns out there's 20 rules about when and how you can call these methods. So I would recommend either using the TCK we implemented for that, or just not implementing it yourself. That's my biggest recommendation. Just use a library which does it correctly. Well, best Akka Streams, but any other one will do as well, because they're all compatible. So reminder of our types. I already showed that in the Akka HTTP case, because yeah, this catch-22 between them. We have sources, flows, and sinks. One difference between other APIs you may notice is you would expect a source to have one type parameter, like it's a source of ints. Well, in Akka it's a source of ints and not used. Okay, this is weird. Flow, okay, int to string, okay, it's a map, right, converts them to string. Okay, that's simple, and then not used again, like what? But it shows in the sink why we do this. Because the sink is, okay, it's accepting strings, and it materializes a future of string. Okay, let's see what this method says. It says sync head. So basically it's taking the first element from the stream and exposing it as a future. So this second or third parameter is what we materialize kind of on the side. The stream gives you back values when it starts running. So maybe this example is a bit boring. Okay, it gives you the first element back. There's many ways to do that, but it's a very clean and it's a type-safe way of doing that. There's no like side channel where you have to mutate some box or do some weird stuff to get values out of a stream. You have a nice type-safe way of doing that. And more interestingly, when we have, for example, a Kafka consumer or producer or anything like that, this would be like a control value where you can set things on it. You can, while the stream is running, you get back this control value, and you can maybe inspect, hey, what is the throughput? Maybe stop connection, increase connections, etc. You have control over the running stream, again, in a fully typed fashion. So, we're pretty happy to see it already adopted widely. I mean, yeah, the frameworks have adopted it, but that's one side of the coin. The other is if people who are not building, toolkits and frameworks as the day job will adopt it. Okay, this kind of still is, but this is a third party. They weren't involved in this Reactive Streams thing at all. When it came out, Amazon announced, okay, we're going to be using Reactive Streams for our streaming stuffs as well. So I'm really happy about that. JDBC next, which may or may not happen in JDK 10. I think it's not gonna happen, is the latest status of it. I'm not sure, keeps changing. Is looking at using Java util concurrent flow. This would be very nice to finally have, JDBC with nicer streaming iterators. It's a bit strongly debated how exactly to use them in there, so we'll see how and when that ships. This was from a proposal, it was using it back there, but we'll see how it ends up finally. And for sure, what's going to be using JDK Flow is the JDK 10, probably going to ship in JDK 10, the HTTP client, which I think is very exciting, because like half of my time at Akka was working on the HTTP stuff, so I'm really happy to see that our ideas with body being the source of bytes are kind of being seen as a good idea and accepted also by the new client API. So we're working and giving some feedback to the Oracle guys there. Looks very good so far. Yeah, again, names. So subscriber in JDK Flow is a sink. In Spring, I guess, would be a flux. And JDK, that's a body processor. So different names, but same protocol. So what's coming this year as a stable thing to Akka HTTP is really HTTP 2, which we have had since last year, but in a almost finished state. Was a bit sad to leave it in that state, but we had to work on some other things. The usual example people show off for HTTP2 is just sharing the connection, right? Here you have normal HTTPS, that's how many connections are opened, and this thing is the SSL handshake. So each connection will be doing the SSL handshake at some point, waste a bit of time. Time to complete around 5 seconds. And this is how the same thing looks on HTTP2. So it's one connection, but multiplexed streams of data. So we only do the handshake once, saves a bit of time, and we can maybe more smartly control how we push the data. This more smartly pushing data is very researchy, and even browser vendors are not quite sure what the best strategy would be right now. So that's more or less an active field of research, how exactly to schedule the delivery of what asset. But what I think is most interesting is, okay, so I'm Akka HTTP, I'm a full HTTP server, and on top of us is the Play framework, which has full control over all the assets, because they have directives. You don't just include a CSS file or an image in Play. You have like a small method call which does it, and then it gets compiled into the HTML. So Play knows what files and assets you're going to be sending down, which allows us then in the server layer to prioritize them automatically. So for example, yeah, we're going to prioritize this HTML, but not the other one, and Play can give us this information. So we're kind of in a unique position to do smart things there. Yeah, push time was a bit faster, but yeah, we'll see how it ends up in real applications. Yeah, as I said, Akka HTTP is the backend for Play by default since recently, since Play 2.6. People always ask about performance. We're on par with Netty backend. We do not have one feature, which is the native SSL implementations, which is kind of important, so at some point we have to do this. But for Play, that wasn't such a big deal because people are used to deploying Play behind something that terminates SSL anyway, like a proxy or like Nginx usually, something like that. But with HTTP2, you're kind of assumed to be terminating the TLS session inside the application, so we definitely will want to implement the native things. Probably just using the TC native things. I don't want to re-implement those, would be a waste of time. So, and finally Akka Typed, which is probably the biggest, most awaited feature of all time in Akka. And I'm curious to see if people who have so strongly demanded it for years will actually enjoy it. Because I think it's a trade-off. So Akka being untyped, the actors are untyped, you can send any kind of message to any actor, actually opens up a lot of niceties in how you design them. You don't have to have a common type for all the messages it receives, but in typed you will have to. So, what's a typed actor? So it's not that one. Forget you ever saw this. This was a misguided attempt at, well, not misguided. Back in 2009, Jonas wanted to show Java people that, hey, look, Akka isn't that scary. And he made this kind of code gen that takes a trait and it generates these message sends based on the methods, right? So it would create a square message with an int and send it in a request reply thing because it's a future. But this looks awfully similar to this, was it Floy? No? What was just showing off? This code gen thing for RESTful calls anyway. Looks awfully similar, right? And this is what we found out about it. It's a really bad idea. It's a bad idea because it kind of leads you down this way, where you have, oh yeah, I just want an option of int back. Oh yeah, I just want an int back. Oh yeah, I just want an int and an exception back. And it just doesn't fit well with distributed computing, where you're not going to get the remote host's stack trace. For one thing, just security reasons, bad idea to do that. For another thing, why would we keep sending over huge stack traces if the thing will be blowing up all the time? It would be a huge performance penalty. And the biggest problem about all these APIs here is the blocking, right? And all of reactive things, everything like Akka stands for is not blocking. So it's kind of goes against our principles. So this was deprecated, that's removed, don't touch it. But it was the first attempt at giving types to actors. Summarize that. The second attempt was typed channels, inspired by ghost channels, and typed by what it can accept, what it will emit. And sadly, the problem with this implementation was, so this is how you would send messages to a channel, this arrow thingy. This is what got Scala infamous for. I mean, there's some libraries in the Scala ecosystem, Scala Z, which do a lot of operator overloading. We don't. So this again didn't quite fit our feel, and the types actually needed Scala macros to properly compile this, and we were not able to express the same things in Java. So we dropped the API because just complexity and not being able to express it in plain Java was a blocker for us. I mean, we have to have feature parity between Java and Scala. So we dropped that. And then a lot of white papers later, because this was still and is still an active area of research, we saw the reactors white paper, which is not to be confused with the reactor framework. Sadly, everyone uses the same names for things again. So reactors was a paper by, is it Martin Alexander Prokopec and Martin Odersky, and they worked on kind of reinventing actors. So it's reactors, not the other kind of reactor that you may think about. And based on that paper and a bunch of experiments, we arrived at this new API, which, okay, this is simple. The actor has a type, and it can only receive this type of message. And we have behaviors explicitly. So if you haven't seen Akka before, the differences may be not so obvious how big they are. And in reality, there's two APIs, and the difference between the first one, so this is typed, so this is Akka untyped, extends actor, and this is Akka typed, where you extend this actor mutable behavior and it can receive commands. And that's still basically the same. You see that on message you get a command, okay, so that's typed indeed. And one thing that is gone is the sender. Previously you saw we had this sender reference. Sender doesn't make any sense if the sender can be different for the message, right? The same message can be sent by one actor or the other actor, and they are expecting to receive different types of messages. So we had to get rid of the sender. And the other difference is that we're going more into a functional side of things here. So this is the kind of mutable API. We call it mutable because here you have a mutable variable. And here you have the immutable style, which is purely functional, so you get an actor context and a message, and you match on it right away. Again, has a Java API. This is the Java API. Again, we provided a builder for it, but hoping to see pattern matching in Java eventually, so then we would not have to build this, these builders. If you're curious about pattern matching in Java, there's a proposal up there. I think it's Project Amber. I don't know its status currently. It's more about, let's think if we could pull it off, I think. But would be nice. And also a nice nod to Scala, I think, kind of showing that, yeah, pattern matching is actually a good idea. So, if you want to learn about Akka Typed, this is the links. And as we're running out of time, just a few things. I'll throw out there what we're focusing on in the next period. So Alpakka is basically, if you know Apache Camel, it's our silly attempt of doing wordplay about alpacas and Akka, so it's kind of a better camel. Better in the sense of having an actually defined threading model. So I've in the past worked with Camel, and the one problem I used to have, and we've heard people complain about as well, is that every module of Camel would be different about how it handles threading and operating it in production when you have a lot of stuff going through it, maybe not the nicest thing. So this is what we bring to the table with Reactive Streams, powered by Akka Streams, obviously, and we provide integrations to basically anything out there, okay, AMQP, all of the AWS APIs, Cassandra's, FTPs, Google APIs, anything really. So, and this is interesting for you even if you're not gonna be using Akka as your primary thing, because this is all reactive streams. So even if you're using anything else, I don't really mind you using something else, but you can use our integrations with any kind of technology. So maybe it's still interesting for you, even if not using Akka itself. Yep, let's jump forward a bit. I think this is the prime point about reactive streams, that it's a ecosystem. So we've created this ecosystem that if we build integrations for stuff, everybody benefits, but also if a database vendor exposes some reactive driver, we also benefit. So it's a kind of nice way to improving everyone's lives. New things, this may be interesting if you have been using Akka. People have not raised their hands here, but let me just give a shout out here. So we rewrote the remoting layer. We used to be actually pretty slow. We would do like 70K messages. Now we're up to 1 million per second. Benchmark setup described at the bottom here. And this is UDP based, but UDP based with sequencing and redeliveries, so basically same as TCP, based on Aaron, if you know Aaron. And we're also implementing right now the same protocol over TCP because we need it for TLS. We thought, let's not reinvent our own crypto. This has never gone well for anyone. So we will accept some slowdown. We've seen maybe half of the performance of Artery on UDP, but you're gonna get crypto because we could pull off datagram TLS on UDP, but it's currently a bit of a pain with how the JDK exposes it, and then we would need to get actual performance, we would have to go native anyway. So we chose to go TCP. This is how you enable it, just works. This is how the pipeline looks like if you're interested. It's basically allocation free except the deserialization step, which is why it can be so fast. And it means 0 changes to your code base. If you've been using Akka before, you're using it now, you change this one switch, you get a 10x performance improvement and less allocations. So, pretty happy about that. I talked a lot about these messages, right? So how do they actually look like on the wire? This is a uncompressed message. This is how a message looks like in ordinary Akka remoting. And the reason we added compression in the recent revision of the remoting is, when you look at this, this is the address of the actor, this is the sender, this is the receiver, and that's the message. Hello. Right, so I talked about HTML, HTTP so big. So yes, this is smaller than HTTP headers anyway, but you know, we could do better than that, so we did. And now a message is compressed, and we do lookup tables for the identities of the actors. And now the message is as big as it should be, right? It's not dominating the size because this is just a small string, but actual payloads are like absolutely dominating the payload now. The entire message. So, and most multi-DC things, basically not much to say except we do support multi-DC awareness and proximity. This is a new thing this year, rolling out next week, basically. Yep. Basically, if you have global clusters, we now support that nicer than previously, which was very naive. And a specific API, which is an extension of a persistence API, but tailored for multi-region and multi-availability zone and multi-DC settings, in which it's not like, ooh, a node has gone down, and yeah, we'll just restart all the things over there. When an entire DC goes down, it's a bigger of a deal. So all the monitoring about it and the mechanisms to dealing with that are slightly different. And again, all expressed in types, and in the event handler you can accept a message here that will tell you if this message was replicated from another data center or if it was directly sent to you. So let me skip over that. This is mostly interesting if you've been already deep into Akka anyway. But the interesting thing is we are able to guarantee basically high availability with like a hot standby, because even without the other data center being sent messages to, it will kind of keep getting the messages in the background, and if one of the data centers fail, the other one is ready. It has all the data and it can already start replicating, start answering queries from the data it has replicated from the other DC beforehand. So differently than what I shown in persistence, where we assume that they share the same data store. This is where you can read about it. This I can skip. When Josh was showing this start boot thing, we have the same. We call it developerlight.com. You just click around, you get the dependencies, you're ready to go. Tracing just works. Metrics just work. Tracing is especially interesting because we integrate with a number of backends, Jaeger and Zipkin, and it works across Scala futures, Java futures soon, not yet, actors, as well as streams. What else? Oh, and HTTP cores. So you have the entire stack covered if you stay in the kind of Akka ecosystem. And this is all based on open tracing, so whatever supports open tracing would also contribute to this trace span. So that's nice. So yep. Summing up, this is where to find more information. Just akka.io and our GitHub. You can always reach us on the Gitter channel, and we'll be probably moving away from the mailing list, which I do like, but to be a bit more inclusive for newcomers, new starters. There's going to be a forum as well this year. This is the link to the book if you wanted to. Just bit.ly, why reactive. No commission. I get no commission from it. It's freely available, so feel free to grab it. And thank you very much. I think I went 5 minutes over time, so I'm sorry, but I'm here and you can ask me any questions you want. Thank you.